So, we discussed the Reynolds transport theorem as part of the fundamental concepts and used that in deriving the integral form of total mass balance, and then use that integral balance to derive the differential form of the total mass balance. Now, we are proceeding towards deriving another conservation equation, we say major conservation equation of importance, namely the linear momentum balance. And first we will, just like the case of mass balance, we will derive the integral balance, integral linear momentum balance, and look at applications of the integral balance. Okay. Okay. Now, this is the outline. Start with the law of physics, okay, and derive the integral linear momentum balance using the Reynolds transport theorem and look at applications. I think the sequence is a little obvious based on our mass balance lectures. Okay. So, what are the applications which you will be able to solve at the end of this integral balance equation, linear momentum balance equation. Okay. And the first example would be if you have a plate and then water impinges on that, and then you are holding this plate, what is the force you should supply so that you hold the plate. Okay. Second example is a nice example. Let us say you have a tank and then it has some water in it. Of course, suppose if you have balance and it gives you the weight, then the weight will reflect the mass of the tank and mass of water in it. But now suppose if you have flow also, then the weight should indicate the effect of flow as well, or the momentum as well. That is what we will see. Okay. How do you formally do that? The third example is where you have a elbow, which is usual pipe joint, and then water flows in and flows out, or air flows in and flows out, and then if you leave it without any support, the elbow will just start moving. What is the force you should supply so that you hold the elbow? Okay. And other example is the flow of let us say air or water through a pipe, and there is loss in pressure because of friction between the fluid flow and the wall. So, how do you evaluate that frictional loss or frictional force based on measurement of the pressure drop and other variables. Okay. So, those are the applications which we will be seeing at the end of this integral balance equation. Okay. So, of course, these are the experimental setups which are familiar, and the control volumes are same, but what is it we are going to account for is now different. We are going to account for the momentum in, momentum out, forces acting, etc. Okay. So, we keep seeing the same control volume, but the balance for which we do that property differs. Earlier it was total mass, now it is going to be linear momentum and associated forces, okay, be it the flow through pipe or this flow through tank. Now, so let us start deriving the integral form of linear momentum balance equation. So, within the scope of this course, when I say momentum, it means linear momentum. Okay. You can derive conservation equations for angular momentum. We are not going to discuss that. We may use it in a very simplified form later on, but so when I say momentum, it means linear momentum. So, we will stick on to that convention and use the word momentum. So, start with the law of physics. In the earlier case, for the case of total mass, it was conservation of mass conservation principle. Mass of system was constant, that is the law of physics. In this case, the law of physics is the Newton's second law of motion. So, that is the starting point for deriving the integral form. Now, what does it state? The time rate of change of momentum of a system is equal to the sum of all the forces acting on the system. Okay. So, of course, we should make note that the law is written for a system. Okay. Now, this Newton's second law of motion is not new to you, it is very well known to you. Only difference is that you would have written this Newton's second law for a solid object, well defined mass, etc. Now, we are going to write an expression for Newton's second law for a system made of fluid. That is how we should view it. Okay. So, let us do that. Now, when we derived the Reynolds transport theorem, we expressed the rate of change of an extensive property of the system in terms of the rate of change of integral. We express this extensive property in terms of integral, where B represents in the present case momentum, mass into velocity, which is an extensive property, and small b would now represent momentum per unit mass, which is the velocity vector. Okay. That is a distinction. In the earlier case, for the case of total mass balance, capital B was m, small b was just unity 1. In the case of momentum balance, B represents momentum, the total momentum m into the velocity vector. So, the intensive properties per unit mass, momentum per unit mass, is the velocity vector. Okay. Should note that both the quantities are vectorial quantities, both the momentum and the velocities are vectorial quantities. And let us proceed further. And so, I like to mention this velocity can be viewed in different ways. Of course, one is of course as such velocity, and in the derivation of mass balance we saw that the velocity can be interpreted as a volumetric flux. Now, we are interpreting velocity vector as a momentum per unit mass. So, velocity can be given different physical significances. One is velocity as such, the volumetric flux, and now momentum per unit mass. Okay. Okay. Now, how do we write the momentum of the system? Okay. Now, this diagram is well known to us. Keep showing this diagram because a very good representation of system and control volume. Moment you look at this diagram, the gas inside and then part of the gas going out quickly gives a quick good understanding of what a system is and what a control volume is. So, now how do we express the momentum of the system? So, as usual what we will do, we will divide the system into smaller and smaller volumes, okay, each of volume delta V I, and each has its own density, okay, that gives mass of each element. Now, earlier we stopped at that because we are interested in the mass balance. Now, we are interested in momentum balance. So, multiply by velocities, each region can have a velocity. Please note that is a velocity is a vector here. So, each region can have a velocity. So, what do we do? Split into volumes delta V I, multiply by rho I, and then multiply by the velocity, you get the total momentum of the system. Now, as usual we want to express that in terms of an integral. So, we consider many such small volumes, and as the number goes up, the each volume tends to 0, then you can approximate this summation in terms of an integral. So, this rho in V dV integrated over the system gives you the momentum of the system. The total momentum of the system is expressed in terms of integral rho V dV. How do you interpret? Rho dV will give you mass and multiply by velocity will give you the momentum. Okay. And this is written in line with the same expression on the left hand side, mass into velocity written in terms of density, velocity, etc. In the case of solid particles, you can proceed in terms of writing mass itself, use mass, continue to use mass. But now, for a case of a fluid, the relevant property is the density, and that is why we express in terms of density. And apart from that, we allow also for the density variation within the system, velocity variation within the system, and hence you have an integral. Okay. That's how we should interpret integral rho V dV. Okay. Okay. So, now let us state the law of physics, the Newton's second law of motion for a system made of fluid. So, left hand side we have rate of change of momentum for the system. As we explained just now, express this momentum of the system in terms of this integral expression. So, the left hand side now represents rate of change of momentum of the system, and according to the Newton's second law of motion is equal to sum of all the forces acting on the system. So, this expression is the Newton's second law of motion for a system made of fluid. And of course, the first observation on this equation is that it is a vectorial equation. It is a vectorial equation. Okay. the left hand side you have V vector, the right hand side of the force vector. That is the first observation. This vectorial nature of the equation distinguishes this equation from all other equations. When I say all other equations, we have seen a similar law of physics for total mass balance, that was a scalar equation. We are going to come across similar law of physics for energy balance and species balance, all those are scalar equations. This equation law of physics for momentum is a vectorial equation, okay, and that has to be kept in mind. Because it is a vectorial equation, what we do? We work in terms of components of that equation. So, let us write down the x component of the above vector equation. What do I mean by that? This velocity has 3 components Vx, Vy, Vz. So, I use the x component alone. Similarly, on the right hand side I have the f vector, I take only the forces acting on the system in the x direction. In this equation has, let us say, I, j and then k component or x, y, z component, we are writing only the x component. So, we will derive the linear momentum balance along the x direction, analogously we can do for y and z direction. Okay. So, how do you read out this equation? This tells you rate of change of momentum of the system, or x momentum or momentum along x direction, and right side sum of all the forces acting on the system along the x direction. So, we associate a direction with the momentum. Okay. Now, as we have done under total mass balance, we will use the Reynolds transport theorem to express the left hand side in terms of control volume, control surface. Okay. So, let us write down the general form of the Reynolds transport theorem, which relates rate of change of property for the system to the rate of change of property for the control volume and net rate at which the property leaves through the control surface. Now, this equation, this forms for any general property. B could take on any values. For the case of mass balance, B was 1. Now, we have seen that B is the velocity vector, and because we are working in terms of x component, B becomes Vx. So, we are going to apply this Reynolds transport theorem taking B as Vx. Now, how do you read out this equation? Rate of change of x momentum, okay, for the system, rate of change of x momentum for the control volume, and then we have always been telling this term, the integral term represents net rate at which the property leaves through the control surface. Now, what is the property? It is x momentum. So, this represents, this term, the integral term represents net rate at which the x momentum leaves the control volume through the control surface. Okay. So, those are the physical interpretations for the 3 terms appearing in this equation. Okay. Now, what do? We use the Reynolds transport theorem in the left hand side of the law of physics, the Newton's second law of motion. Of course, we use substitute here, okay, and then express the left hand side in terms of control volume and control surface. Right hand side is the sum, sigma represents sum of all the forces acting on the system. That is why I used a sigma there representing sum of all the forces. What are those forces? We will see later. Okay. So, what is that I have done? This taken the law of physics, use the Reynolds transport theorem and express the left hand side in terms of control volume and control surface. So, once again want to emphasize that the right hand side, the force term comes from the law of physics, What Reynolds transport theorem does is to replace the left hand side, which is in terms of system, in terms of control volume and control surface. The force term does not come from the Reynolds transport theorem, it comes from the law of physics. Okay. The left hand side term expressed in terms of control volume, control surface, that part only comes from the Reynolds transport theorem. Okay. So, now the left hand side is fine for us because it is in terms of control volume, control surface, right hand side is in terms of system. Okay. So, like we did for mass balance, we will express that in terms of the control volume. Okay. So, how do we do that? we use the concept of coincident system and control volume. So, we have seen this a few times, and the derivation to begin with, we took the control volume and system to be coincident with each other at every instant of time. That is shown in a different way in these three diagrams. The system is just entering here, it is exactly coinciding, system has partly left the control volume. So, we take the condition at time t where the system and control volume are exactly coinciding with each other, and that is what is shown separately here. So, what happens because of that, the boundary in terms of volume and surface becomes same for both the control volume and system. So, whatever forces acting on the system and forces acting on the control volume or the contents of control volume, both are same. Okay. And of course, we have our own animation which shows that we take the instant where the system and the control volume coincide at time t. Okay. Yeah, that is the point where we take. Okay. So, now let us express this in terms of equations. So, let us carry over the integral equation which I have written in the last slide. The left hand side in terms of control volume and control surface, and right hand side representing sum of all the forces along the x direction is for the system. We consider coincident system and control volume at time t. These are instantaneous equations. So, at every instant of time we consider system and control volume to be coincident. So, now I can write sigma f x, sum of all the forces acting on the system, of course x direction, is equal to sum of all the forces acting on the contents of control volume. Okay. We may just say on control volume, but to be more precise we should say contents of control volume. So, now which means that the above equation I replace the right hand side which was in terms of system in terms of control volume. Okay. So, now this is the integral form of the linear momentum balance. It is all in terms of control volume, control surface. The right hand side is also in terms of control volume. Okay. We have derived for the x component. Similarly, we can derive for the y component and the z component. So, we should always keep this in mind. It is a vectorial equation. It has 3 components, and we are in the examples to follow we will be using the x component, y component and so on. Okay. So, these in fact 3 put together form the set of equations which constitutes the integral form of linear momentum balance equation. Okay. Now, let us look at the significance of the terms in the linear momentum balance equation. For the sake of significance, we will rewrite this equation slightly differently. We will write V x here, and then similarly here also we will write V x here, just for understanding and interpreting the significance. Okay. Now, the first term is a transient term. It is the time rate of change of momentum within the control volume. We have d by dt here. So, time rate of change, and this represents the integral term represents the momentum within the control volume. So, the first term represents time rate of change of momentum within the control volume. Okay. The second term, this integral term represents net rate of flow of momentum, of course out through the control surface by convection. We have always been saying that this represents net rate of flow of property. In this case, it is the momentum out through the control surface by convection. We have already seen what convection is. I will explain shortly again. Right hand side we have sum of external forces acting on the control volume. Okay. Here I use the word momentum, but to be more specific, this momentum represents the x momentum. Analogously, the force on the right hand side represents the force in the x direction. So, momentum is also in the x direction in the left hand side, whether it is in the accumulation term or in the flow term and the convection term. On the right hand side also force is also x direction, similarly y and z directions. Okay. And as I have been telling, forces acting on the control volume, to be more precise, forces acting on the contents of control volume. Now, we have looked at this experimental setup with the control volume and so on. Now, our control volume was something like this. Okay. Earlier we looked at the control volume and accounted for mass in mass leaving. Now, we look at the we use the control volume to do a momentum balance. So, we account for what is the momentum entering, what is the momentum leaving. So, if you look at the, let us say you look at the pipe and say the pipe carries water, one way of saying it says pipe carries water, let us say colored water. Next step would be saying that mass enters the control volume and mass leaves the control volume. Next step would be saying that momentum enters the control volume, momentum leaves the control volume. So, what you see is of course a experimental setup with a pipe, but the way in which you look at it differs. At the superficial level you can say just say water entering, water leaving, but that water which is flowing carries with it mass, that is what we used in the earlier case. Same water carries with it momentum and you are now doing a momentum balance for that. So, we say that that stream of water carries mass with it, that stream carries momentum with it. Later on we will extend this to energy and then species. So, when I say convection, this physical picture has to be kept in your mind, whatever is carried by the stream because of its bulk flow. So, with this term either is called convection or by bulk flow, both mean the same. Okay. So, now let us compare this integral total mass balance and linear momentum balance. The way in which they are derived, significance are all analogous. Let us compare both of them in this slide. Okay. So, that is the integral mass balance. Even the terminology words used are all analogous. Okay. The first term represents time rate of change of mass within the control volume. Second term, net rate of flow of mass out through the control surface by convection. Okay. Right hand side is 0, for the case of mass balance it was 0. Okay. Now, let us write down the integral linear momentum balance in the x direction. Look at the significance, you can almost write analogously time rate of change of instead of mass it is momentum, x momentum within the control volume, and then net rate of flow of momentum out through the control surface by convection. You have mass here, of course total mass, here you have x momentum. Similarly, here mass leaving through the control surface, momentum leaving through the control surface. Okay. And right hand side, unlike the case of mass balance, we have external forces acting on the contents of control volume. That is of course a difference, rather big difference. Unlike it was 0 earlier, it is sum of external forces acting on the control volume.